In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force.
All right, hello and welcome everyone. Today we're going to be doing the history of wave invariance. We're going to be going over ether theory and then relativity theory, doing a little compare and contrast on some of the math there, and just kind of going over the historical narrative of everything and learning what both of the theories were about, what they offer, what problems they were trying to solve, etc. So in the modern times for relativity theory, we're told that the speed of light is a physical constant. So we're going to be, by the end of this presentation, we're going to look at how they came to that conclusion, what principles that was derived under versus what the ether theory would predict. And then what it's going to turn out to show is that relativity theory requires reciprocal transformations for equivalence. So in other words, the speed of light has to be constant in both frames, which leads to some contradictions. And most of the evidences that are put forward as proof of the theory are actually only one-way measurements with no reciprocity. So they're up for grabs for an ether interpretation. And it just so happens that they're going to have the same exact framework as relativity theory, but we'll get to that as we go through the whole Prezi. Okay. So the constant C of C under transformation is really just C plus or minus V on the one way. So without the reciprocity, it's just with respect to the elastic medium in which it was derived under. So a nice useful tool for more in-depth breakdowns of these same concepts. There's a YouTube channel called @itsbs, and his Twitter is also its_bs. You can hit that guy up for sources and diagrams, videos, etc., breaking down the subject and the intricacies of it. Well, but once you get familiar with it, it's pretty straightforward to understand. All right, and then here's Einstein writing how the speed of light is constant, and it's actually equal to c. So we'll keep going here. So starting off with the from 1727, a man named James Bradley used a ratio of the speed of light over against the ratio of the velocity of Earth, and came out with 20 arc seconds. So that's known as stellar aberration. And this is dependent on the finite speed of light here as a physical constant propagating in a vacuum with no deviations or anything like that, to produce this interpretation where Earth's motion is actually responsible to be the cause of this measurement here. And this is the only measurement where they ever had a ratio of 30 kilometers a second come out to something that they measured terrestrially. Now, they get it. We'll cover Airy's failure and stuff later, but as we go through, we'll just take the narrative as is and see what they come up with. So when they measure aberration in air, in other words, when they just have a zenith mount telescope and they look up, there's a deviation from what they expect, and that comes out to be 20 arc seconds over the course of a year. And again, giving them the 30 kilometer arc second ratio when you do the arctan of that for the V over C. Now, the next up, the measurement alone in air can't really differentiate if we're moving or if the sky is moving or if there's a medium in between us and the sky that's causing the aberration. So in order to determine whether or not, which one of those models is true, we need to manipulate one of the variables. So what we can do is we could slow the speed of light by introducing another medium inside of the telescope, and that's going to slow the speed of light, and the Earth moving at its near constant velocity of 30 kilometers is going to be able to travel a slightly longer distance as the light is slowed from the eyepiece to the beginning part of the telescope, and that's going to increase this angle here as a function of the reduction of the speed of light and the constancy here. So if you make this 0.75 C instead of this constant, its normal value, this angle would increase to 28 arc seconds instead of 20. So if Earth is the causal mechanism here, they would expect an angle increase. And let's see, in 1853 is when Arago published his findings, but he actually did the experiment in like 1810. So 1810 here, so we started in 1727. We're in 1810 territory now, and they decided that, well, let's put a test to this and see what we can come up with, or let's manipulate that speed so we can see which is moving. So Arago puts a crystal prism and half covers his telescope, and when the star transits the center of it, when it intersects with that crystal prism, there should be an angle increase to keep the star in the center of it. And what he measured was that there was no change when the light entered the crystal prism. And the conclusion from that was that the refraction index of a moving medium is the same as a stationary medium. It's a pretty interesting and generous conclusion, but that's what they went with. And then we're going to go over some experimental contradictions to that as we go forward. But right now they try to explain this experiment by saying that perhaps there's ether that's trapped in the telescope or the crystal prism, whatever would be holding the medium. In this case, it would be the crystal prism. So there would be ether trapped inside of here, and it's bouncing around, and it carries the light in the opposite direction of motion, such that it cancels out the increased angle and makes it appear the same. And then, of course, later on, they finesse that up a little bit with a Lorentz transformation, but we'll get into that as we continue through the history here. Now, what we need to learn about next is Fresnel drag, which was an experiment done by a man named Fazal, otherwise known as Young Fizzy. What Young Fizzy came up with was that a moving material translucent medium would carry ether in it as a as a proportional ratio to the square of the refractive index itself. So what we're looking at here on this side of the equation is just C plus or minus V, and then C over N is just the refractive index. So that's going to change the speed of light, and then it's going to be plus or minus the velocity of the medium going with or against the medium. And then of course over here we have the final amount of how much drag there's going to be based on the velocity as a function of the square of the refraction index. So in other words, the more refraction, the higher the refraction index of a translucent material, the more is going to be drag. You would expect more drag or more resistance in either direction depending on where you're going with that. And of course, he derived that under the principles of an elastic ether, where the density in the material medium is proportional to the square of the refractive index. So this is what they were working with back then. And then, of course, they experimentally measured this here, but we'll get to that in a second. But I want you to pay attention to the concept of deriving velocity of something as a function of the medium. So in classic physics, you can determine the speed of a wave in an elastic medium by taking the elasticity over the density, and the square of that will give you how fast the wave can propagate in that medium. In the same respect, you can derive the speed of light using the vacuum constants epsilon and mu, which are the electric permittivity and magnetic permeability constants for a vacuum. So the inverse of this value here gives you the speed of light, which is really awesome. So the same exact principles here. And then we need to learn about the Doppler shift. So as these people were finding out that they could use the speed of light in ratios like this, they also found that it was a perfect description for Doppler shift. So Doppler, Christian Doppler, starting out with the speed of sound in air, came up with these equations here, and what they actually, with no change at all, just changing the velocity component, obviously, for the rate of the wave, it actually works for electromagnetic propagation as well. So there's not like a special one for EM propagation versus sound or whatever. It's all the same. You just put in the different speed for the wave that you're using, or for the speed of the wave in the medium rather. And that will give you the correct amount of Doppler shift. So if something is moving towards you, you're going to hear a higher frequency pitch. And if something's moving away from you, you'll hear a lower. That's the classic red and blue shift, all described by these equations here. And we'll get into some diagrams that show what each one of these means here as we continue, so we can put some faces to the names here. But well, we already went over the Christian Doppler and came up with these equations, and then obviously derived under the principles of an elastic medium for ether as he goes on. But here what we're looking at is a spherical wavefront emitted from a source that is stationary. You see these nice symmetrical equidistant wavefronts being emitted from the center, creating a nice sphere here. Very nice. And this is when the velocity of the emitter is 0. As the velocity increases, you see here that the observer, or the detector, or the emitter in this case, is emitting an ellipsoid wavefront. Like this is what he would perceive in his frame. This ellipsoid. This is what creates the high to low frequency pitch based on where your position is as this traverses either parallel to you or transversely. And then, of course, as the speed increases here, you start to exceed the information that is received. So what we're looking at here is, say you're an observer here at 0. This is traversing by you. You would see this object pass you. You wouldn't hear it, and then there would be a delay before you hear it. This is what this equation describes, and this is what the wavefront would look like for the emitter, traversing at that speed. And then, of course, we have supersonic here, which is where you're breaking the sound barrier, and that's where, I'm sorry, that's where you're actually going to lead the sound there. But same concept, just showing how that wavefront changes now. Now it's like coming in a backwards cone emission relative to the emitter there. So you can see the importance of how these equations describe what the what the emitter is emitting, and what their wavefront looks like for the observer that's measuring it. Now, really important concept here, because they use Doppler shift for radar. So if you've ever got a speeding ticket and they clocked you, well, they did that via the mechanism of Doppler shift, and we'll get into that a little bit as we continue. So an important thing to note is that you can use electromagnetic propagation and the change in frequency to determine how much velocity there was that changed the frequency, because there's a proportional ratio. So as long as you know the starting wavelength that was sent out, the changed wavelength will tell you how much velocity there was to create that difference when it hits the object and gets reflected back. So really simple concept there. And then here they actually have it cataloged for every velocity starting at 1 mile an hour and upwards. They actually know what the beat frequency for that is going to be. And the beat frequency is, of course, that change in the starting wavelength there. When it returns back, that beat frequency is going to be the change in the frequency that's proportional to that velocity. So every velocity has its own beat frequency. And once you've identified the beat frequency, you immediately know the velocity. So that's what we have here. We have a table of speeds, 100 miles an hour, 70, 40, and you could see what the beat frequency comes out to and what that is in the percentage of hertz. So you can just kind of see the relationship there. But you can see directly how velocity affects how the observer measures the speed of light. Now here's some patents regarding the different speedometer technologies. So there's the classic speed gun where you have to be stationary to get the measurement, and then there's a patent for one that uses 2 signals. One shoots down at an angle, so it bounces kind of off the ground, and that produces a stronger red shift. And what that will do is give you, they can determine based off of the stronger frequency that that's your velocity. So they subtract that out from the one that has the weaker signal, and that beat frequency is going to be the velocity of your target. So an interesting fact about this situation is, like, I'm sure we've all heard the meme or the story of, like, how to beat a speeding ticket, you just ask when the gun was last calibrated or whatever. Completely irrelevant. The gun will always tell you what frequency was emitted, and as long as you have that frequency, it's going to be the beat frequency is going to be proportional to that change, giving the velocity. So the time in which the device was calibrated is completely irrelevant, because all these are, in other words, this is like hard-coded features of electromagnetic propagation and velocity. Based on how fast you're moving, you're going to measure that change in wavelength directly proportional to that velocity, 1-to-1, V over C, as noted in the classic Doppler equations here. All right, so that was Doppler shift back in the 1842. So now we're going to move on to describing that experiment that Fresnel came up with, where he had that equation to describe the propagation rate in a moving medium. and how that'll affect the speed. So a man named Fazal built an interferometer, one of the first interferometers ever built. He split a beam of light to go with and against a flow of water in these tubes here, and we could see how this affects the velocity of the propagation. Second, so we can see how this affects the propagation here. When the light beam recombines, if there's no effect due to the velocity of water, then these light beams should recombine on the other end and produce no fringe shift pattern, meaning there should be no destructive interference pattern created because the wave, even though it's split, returns in phase because it's the same that it started with. So if there's nothing affecting it, there should be no fringe pattern. But what they measured was that there is a fringe pattern, and when you square the distance of that fringe pattern, that's actually proportional to the velocity that caused it. So they had the water moving at like 10 kilometers a second, let's say, and then this fringe pattern, when you measure it out based off of the original wavelength, when you square that distance of dark space in the fringe, you will get the velocity that produced it. Now, what he found here is that there is an 88% proportional ratio to the moving water. You get 44% of a reduction going against the moving medium and 44% of a boost going with it. So 88% of the velocity of a moving medium is translated with this equation. This is what was experimentally validated with this equation 18 year or that was derived in 1818 and then experimentally conducted in 1851 here. So and remember, the principles in which it was derived was under the principles of an elastic ether, and then the ether inside of the medium being proportional to the square of that refractive index. And they started measuring refractive indexes and things like that using fringe patterns. When they would shine light through it, they would see different rings or fringe patterns. So you could look at like a Newtonian ring. There's several different types of fringes that are produced in that way, but based on the fringe gaps in the ratio for the speed of light, this is how they came up with all of this stuff. So here, all they've done is just introduced a velocity component to the moving medium, and then what do you know? That actually increases it at a proportional ratio to the tune of 88%. And then next up, although this experiment was conducted in the 70s, it is directly related to the original Fazal experiment, because here we have transverse motion, which we'll get into in a second. So this first experiment is the longitudinal form, where you're traveling parallel to the flow of motion. So this water is flowing, horizontally, let's say, and this beam of light is propagating horizontally once it hits the interferometer beam splitter and all that. So it's going in that direction of motion. Now, when you're transverse, you would be perpendicular to that direction. So in other words, if you're stationary, right here in the middle of the screen, there's going to be movement going directly across the screen. So you're perpendicular to that. So the classic prediction was that, for Doppler shift at least, was that there would not be any change, because when you're when you're perpendicular to motion like that at that center point, there's no change in distance, meaning the wavefront should hit you symmetrically, so that there's no that cone that we were looking at earlier, that ellipse shape shouldn't be present when it's directly perpendicular to you. And then on top of that also goes into plays into Airy's failure and Arago's experiment, because their interpretation was that it's not affected, it gets canceled out, etc. So we're going to look at this experimental setup that Jones came up with in the 70s. And here we have a rotating disc of plastic, and we have a source. It sends light down to the source, and it hits a 45-degree angled mirrors, and it goes back up to a detector. Now, if the speed of light, if there's no ether, and the speed of light is independent of all that, like relativity says, then when this is going clockwise or counterclockwise, the fringe shift pattern should change in the direction corresponding to the motion, because if relativity was true, then the speed of light would be dependent on that motion there. But what was actually measured is that the drag is always positive regardless of the direction of motion. So it doesn't get retarded in the way that it would have to be directionally dependent if there's no medium to facilitate that. And that's an extremely important distinction between the two theories, because one makes a prediction that it should change in the opposite directions, and it actually doesn't. It's always positive. So what that means is when they say that Aries failure is confirmed by Fresnel drag, right? That's actually a lie, because Fresnel drag, with the reduction of the speed of light, is going to change just based on the refraction index alone, before you even introduce the 30 kilometer a second velocity component, is going to increase that angle to 28. The velocity component is going to change the decimal placage of it. So it's still going to be in the 28 range, but they actually measured no change, so it still remained 20. Huge problem for them, especially in the face of this transverse experiment that shows that there absolutely should be a change regardless of it being longitudinal or transverse. And here, Jones is just talking about the significance of that situation, and how it played out, being proportional to the square of the speed of the rotation. So an important thing to note here is that these fringe patterns, right? Even if there's no medium here, let's say, they produce a fringe pattern. So what this would imply is if this device is orientated north-south and then the longitudinal arms are east-west, that means that there's a bias in the speed of light in the east-west directions that's creating this fringe pattern. And then you could square the distance between that and get the velocity component, which is what they did in MMX, which we're going to cover earlier. But but understanding the fringes and the ratio and the proportional ratio to the square of the fringes is extremely important, because that's this velocity component here. This is what this would look like if you measured it in destructive interference rather than measuring the frequency with electronics and stuff, because they didn't have electronics back then, so they would use the square of the fringe. All right, now continuing on in 1862, this is a pivotal moment here, because there were a couple of theories about how light propagates. One was the emission theory, the other one was the undulatory theory. The emission theory predicted that the speed of light in a medium would actually accelerate, so they would multiply by n instead of divide. And so what that would imply is that if so let's take Arago's experiment, for example. When they introduced the medium, instead of being 20 arc seconds, they predict it would be lower, because the light accelerated. So they predict that it would change, in the opposite direction. So what we have here is a setup from Foucault, and then this was later repeated by Michelson a number of times with different configurations and more, more sensitive equipment for more accuracy and stuff. But they all derive the same thing and whatnot. But the purpose here, they have a light source, a rotating mirror, and a tube of water. And what they found was when the light would reflect back, in empty, when this was empty, is that the angle would increase proportional to the velocity of the rotating mirror. And then when they added water to it, this was the deciding factor for falsifying emission theory and validating undulatory theory, which is the wave theory, which is where they would divide by the refractive index to slow the speed of the wave. So when they added water here, the angle still increased, and then it also increased proportional, with that same ratio to the refractive index. So measuring the exact same thing, but now they're just using a rotating mirror instead of using moving water through longitudinal pipes or whatever. And this gave, so they knew how to correctly interpret the Airy experiment. Now we're often told that just the measurement alone, the fact that it doesn't change, is proof that the Earth is in motion. And then they get into the different relativistic ways to describe that. But before we get to that, keep in mind here, we have experimental verification from Foucault, and later in the 70s from Jones, showing that when you add the medium, there's the angle change, and then also the velocity component is carried, whether it's transverse or longitudinal. All right. So in 1865-ish, we have Maxwell deriving the speed of light using the inverse of the vacuum constants here. So 1 over the square of mu and epsilon here gives you the speed of light. It's a very, very awesome concept and lends itself to the physical properties of impedance dictating the speed of light. Because when you get into how Maxwell derived everything, he thought that there was an ether made of rotating vortices that were spinning at the speed of light, and then the centrifugal force from that would carry the wave through the medium at this speed based on the inverse of this of these constants. Very cool stuff. And then here we have just Maxwell talking about that and how all of that was derived and how it's affected in supporting the undulatory theory, all derived under the principles of an elastic medium. So that's extremely important. And then he gets into how this explains polarization and all that in a vacuum. So that there's an underlying fundamental medium to facilitate all that. And again, I just kind of was reiterating here the ratios used to derive the speed of a wave in a medium. Same exact formalism here. All right, now this experiment here is one of the lesser talked about ones, but a man named Hoke in 1868 did a larger interferometer experiment, but mimicked the original Fresnel setup. So here he used a half covered shield for the interferometer. So one arm is shielded and the other one is not. And the shielded arm is filled with water. And the hypothesis was that, based on their interpretation of the refractive index of a moving medium being the same as one in motion, even though they had already measured the change, but this was to substantiate how they interpreted the that the ether inside was like canceled out because it was bouncing around in the interferometer. So if there was no change here, if there was no fringe produced, they concluded that that was proof that the Earth was in motion and that the ether was being carried in the opposite direction of motion, which sounds antithetical, completely backwards, I'm sure, but this is how they had to justify their continual conclusion that the Earth is in motion, despite the fact that every time they tried to measure it, they never got a velocity component that they needed to, except for that one time in air with aberration. But so that was the conclusion of this, that there was no fringe produced, and that was therefore verification that the Earth was in motion. And then also this marked the fact that based on this ether canceling effect, this meant that you could not have a first order measurement of the velocity of Earth through space because the ether was real tricky and it was canceling it out. And that's extremely important because the fundamental baseline, I'm not going to go all the way back to it, but the fundamental baseline starting with Aries is a V over C relationship. That's an absolute velocity ratio. It's V over C. That is a first order measurement of a 30 kilometer a second drift. That would be the interpretation of it. And then here they're concluding that you actually can't measure first order effects because of the ether is very mysterious. Once you put it in this chamber here, it starts carrying the light in the opposite direction. So this is how they interpreted that the Earth is still in motion and that they could not make first order measurements of Earth through space. Now we have Airy coming in 1871, who added water to his telescope, and he had a zenith mount built here, and it actually swivels on both sides here, so you could basically what he was doing with this is he was taking readings on the left and then rotating it 180 degrees, taking it from the right, and then taking the differential of that to average it out to increase the accuracy. And so when he took his measurements 6 months apart, he found that the aberration in water is the same as aberration in air, and that's what he says here. He goes on to say, I think myself justified in concluding that the hypothesis of Professor Clinkerfuse is untenable, and we'll come back to old Clinker here in a second. Had it been retained, the aberration to be employed to the corrections would have increased by 15 arc seconds and minus 15 arc seconds, respectively. So, in other words, a total of 20 arc seconds and change when they add the water, which is close to their 28 value that they, excuse me one second, that they would have predicted doing that. Because this would add up to 30 kilometers a second here for them to get that. But it didn't. So he just states that it was the same and that his hypothesis is untenable. So let me see. I didn't I didn't include his hypothesis. Okay. So Professor Klinkerfuse's hypothesis, and the reason that Airy did this experiment was that Klinkerfuse's hypothesis was that if Earth's motion was real and not an apparent effect, that when you add water to the telescope, it would, it would reveal that the Earth has more time to travel, and that's going to increase the angle. And he says that this is independent of any ether theory, etc., because all he's using is Snell's law and the speed of light. So there should be no ether effects. And if there are, and he said if there are any ether effects, we can figure out that stuff later. But just on the face of it, if the motion is real and not an apparent effect, there has to be an increase. And then he put turpentine in his zenith mount telescope, and he said that in that refractive index, he measured an angle increase, which would fully substantiate Earth moving through space, and that would be a great proof, or that would be great evidence to support that. And so he was like, okay, well, let me confirm this. So he did his with water, no change, and then he just wrote off the whole thing, and that's basically the end of it. Now, after that, there was one more saving grace attempt, because this would be a first order V over C relationship, remember? So they're like, there's no V over C, you can't do it. The water's bouncing around in the telescope, yada yada. So that was the explanation that they went with and concluded to rectify the fact that there was no angle change. So we're going to take a look here at the beginning of the Michelson-Morley paper, where he gives a recap of the situation with Airy's failure and whatnot. And here he talks about the discovery of aberration of light, and then how that affected the emission theory, because the water or light doesn't accelerate in the medium; it actually gets reduced. So that was the falsification of that. And then he goes on to say, for if the tangent of the angle of aberration is the ratio to the velocity of Earth to the velocity of light, then the latter velocity in water is 3/4 the velocity in a vacuum, and the aberration observed in water in the telescope should be 4/3 its true value. So the angle should increase. And what he says here, down at the bottom, we see this little cross here. He's got a little note for us. What's this note say? It may be noticed that most writers admit the sufficiency of the explanation according to emission theory, while the fact, while the fact, while in fact the difficulty is even greater according to the undulatory theory. Oh, no way. Why is that? For the emission theory, the velocity of light must be greater in the telescope, and therefore the angle of aberration should be less. Hence, in order to reduce it to its true value, and what he's saying here by the true value is to keep the angle the same, we must make the absurd hypothesis that the motion of the water in the telescope carries the ray in the opposite direction. So there was a back and forth from Fresnel and Stokes, who were writing Fazal when he did his experiment, and they were trying to say, oh, it's carrying in the opposite direction. That was the premier school of thought to explain this at the time. So insert 1881 and 1887 respectively. Michelson and Morley came up with an ingenious experimental setup for an interferometer that would cancel out this first order canceling effect, and maybe they would be able to measure a second order effect in the drag. So with this setup here going at a cross and going on a there and back trip, the hypothesis was that after it traversed this there and back trip and the first order effect was canceled out, there would be a little left over on the second order from the return trip. So what they had expected to measure using the V over C ratios and stuff, which we'll go over here in a second as we continue, but just to plot out what they expected to measure, they expected to measure a fringe shift that when they squared the distance between it, it would be proportional to 30 kilometers a second. So what that looks like plotted out on a graph would be this dotted line here in the in the west direction, and then going east, it would be it would be retarded by the same amount, essentially. So this would create the 30 kilometer a second ratio for the displacement for the for the fringe pattern. And then what they actually measured here is this solid line. So they measured just over one fringe, which is only proportional to about 6 to 7 kilometers a second, rather than the illustrious 30 kilometers a second. Now, because they couldn't get that 30 kilometer a second ratio, they, end up not Michelson Morley, but the mainstream school of thought says that this is a null result and they actually measured no change and all that, even though we're looking at a positive dip in the west direction and then retarded in the east direction. Exactly. And then to a magnitude that's higher than their air margin. So they actually had a sensitivity and air margin of 2 kilometers a second. And remember, they measured 6 to 7 kilometers a second there. So this was too big to be answered by the first order canceling out effect and too small to validate heliocentrism. So the only thing that they could do here is say, experimental air and or that there was no change and that this is proof that the speed of light is constant, even though we're looking at a difference in the east-west directions here. Oops, I actually didn't. Oh, it's right here. Sorry, I skipped over that. It was on this side of the page. So an important part of how they derive this ratio, what we're looking at here is we have the velocity of light, which is represented now by c, but here they were just using capital V. And then we have the little v or nu, I think it is. So nu here represents the velocity of Earth. And when we ratio that times the distance of the path length that light has to travel, we get what the change in wavelength would be based on that velocity. So similarly to how all velocities have they can map out the beat frequency and how that's going to affect the wavelength of light that you're going to measure based on velocity. This is the exact same way that you would do this, because the output of this is going to give you the change in the wavelength, because the speed you enter here is the wavelength times the frequency, which gives you the speed of light, and then that ratio change based on the velocity and the distance that it has to travel will give you that changed wavelength and frequency that you can compare to the original, and that gives you that velocity component. That's the relationship there. So another thing to note here is that this equation is actually just the same as the Sagnac equation, which we'll get to as we continue on here. This 2D, so 2D describing the geometry of the apparatus, accounting for the there and back return trip of the distance. So just multiplying that by 2, and then over v squared, so the velocity of Earth squared over c squared. And this is just a higher order ratio, looking for that smaller change effect based on the return there and back trip as the light traverses the plane of the interferometer here. And here's the interferometer setup. We got the source, beam splitter, mix across. We're looking at a top-down view here of the path of light. And then once it gets recombined, if the speed of light is isotropic, then this line here should actually just be a straight line across. There should be no dip in the east-west directions. But here we're saying velocity boost and velocity reduction here in the east-west directions, just not to the tune of which they needed. All right. And that was in 1887. And when 1888 rolled around, there was a man named Voigt. And what Voigt put forward was, it was Woldmore Voigt. And what he derived was the early Lorentz transformation, but it's actually just a Voigt transformation. So he starts with the principles of deriving the speed of light under an elastic medium, comes up with coordinates to do a transformation, basically describing a transformation from the perspective of the light frame. So the ether frame would be where the speed of light is constant, and then you would transform from the observer frame to that frame. And in doing that, you're going to get your change in wavelength described. So this theory or this framework inherently has an asymmetry built into it. It's the purpose of it is not to show that the speed of light is a physical constant. It's only constant with respect to the to its inertial frame, which would be the ether frame, conceptually. So that's what they're working with mathematically here. They're not he never asserted that the speed of light is actually invariant, meaning that it's a physical constant that, would remain unchanged under transformation. The purpose of this was to show the asymmetry, because the motion was relative to the elastic medium in which he derived the coordinates for everything and the velocity for how fast the waves and stuff should propagate through it and all that to get the change from the original starting point. So what we're looking at here is the first rendition of the Lorentz transformation, which you'll notice here that the coordinates describe the change in the y and z axis here. And it's also dividing by, he divides by by the gamma factor instead of multiplying for that. And the reason for that is that this is for the transverse equation. To get the Lorentz factor, all you do is multiply all the coordinates by gamma. It'll cancel out the ones where it divided for the transverse, and it'll put a multiplying gamma on your x-axis and your time axis. And in doing that, you get the exact Lorentz transformation that's used for longitudinal. So contraction and dilation in the direction of motion, exactly equivalent and derived 18 years prior to uh, what Einstein says that how he independently derived it. Extremely important concepts here. So again, we're just looking at the finalization of the modern Lorentz transformation, and all of these variables, like I said, were already derived. And the physical interpretation here that kind of confused everyone is this right here, where we have tau equals time minus the distance over the speed. And what this would physically imply, like it's mathematically correct, but what it would physically imply is that time is dependent on your velocity and position. That's not at all what he was saying. This describes the timing and frequency change of the wavelengths of light as a function of a observer moving through this elastic medium. And then the transformation, of course, would show the original wavelength in the ether frame. So that's what the purpose of all this was. And then, like I said, to get the direct equivalence for the longitudinal form, you just multiply everything by gamma, and then the form takes exactly what Einstein writes in his paper and what also Lorentz used. Because Einstein wasn't the first person to actually use this framework. A man named Henrik Lorentz and Fitzgerald were using this framework. They just multiplied by gamma instead to do the transverse. I'm sorry, to convert the transverse to the longitudinal, because they were doing experiments with the electron, and they were basically saying like, okay, well maybe as they were describing it, they described it as a change in the frequency and wavelength of the electron, and they hypothesized that because material matter is made up of electrons, that this physical change in the wavelength may constitute a physical change in material matter. So they were like, maybe this maybe this means that motion of a rigid body through ether, it'll actually be contracted by the square of the velocity that it's moving over the square of the velocity of light. Now, keep in mind the measurements of the wavelengths and the time. So basically, the change in the wavelength and frequency substantiated. That's easily measured. They have the wave. They you can get a fringe pattern out of an electron instead of it being like a ballistic thing or whatever. How they try and conceptualize it in. It produces a fringe. So using that change in the timing and the spacing of the wave, they were like, okay, well maybe that also affects material matter. So the hypothesis that an explanation for Michelson-Morley could be that the device was contracted, that was just like the physical mechanism of that is based on ether theory and the compression of the wavelength itself that the electron is made of, and the frequency. So yeah, this is them just kind of reiterating that and talking about it. And then here we have in 1897, we have Lamore deriving a dynamic theory for electricity and magnetism with respect to a luminiferous medium, or in other words, an elastic medium. And the equations he uses over here, the important ones, is this half order gamma term here. Now, this is going to be said to be mutually exclusive to relativity theory here in some experiments after 1905, where Einstein proposed the same exact framework and ratios as an ether theory with no medium, and making the transformation relative to another moving observer rather than the original wavelength with in the rest frame of the ether. But basically, this half order gamma term here comes from being derived under the principle that motion through the medium is going to retard the wave by a tiny amount, regardless of the first order effect of it. So he's saying that there's just going to be like a much smaller effect, and this is where that part of the equation comes from. Now we're going to look at the equations for link contraction and time dilation. So we have the time gets multiplied by gamma. Lorentz contraction, length over gamma, and the Lorentz factor here is just the reciprocal of the speeds of the uh, of the velocity and then over the speed of light. So giving how much contraction there's going to be. And if you guys want to see an awesome video showing like the actual figures for contraction and whatnot, recommend going over to rumble.com/fe men of stone. Click on a couple of thoughts about the speed of light. I think that's the one. And or it might be a couple of thoughts about Einstein. But yeah, click on that one and you'll see what these look like graphed out, at different velocities in the actual change, in the supposed actual change in material matter based on velocity. And it's, you know, pretty absurd, but once you see it to scale, it really highlights the illusion.
I would actually recommend both videos. The one about the speed of light refers to Marmay's work and the anisotropy of light,
Mm.
and the Einstein refers to what you just covered here. So yeah, I recommend both.
Yeah, they're both fantastic videos. And then especially when you see the contraction to scale, you're just like, oh, okay. I see what you're doing here. All right. So Einstein comes through in 1905 and he doesn't cite anyone. Now, keep in mind, Lorentz cited the Voigt transformation and he was like, yo, I'm actually just using Voigt's framework, going to multiply these out. And this is, how we're going to use it. Einstein, no citations, acts like he completely independently derived that, or, the story goes that he independently derived this and then looked for some previous experiments. And then based off of how those played out, they, quote unquote, confirmed the physical invariance of the speed of light. And the physical invariance, of course, meaning that the speed of light is a physical constant and under transformation, it remains constant. And what an observer would measure in a moving frame is that there would be no change. So in other words, your interferometer should measure no velocity change. And uh, that's how they answered the Michelson-Morley experiment, by removing the medium, making it relative to, the sun, and then doing transformations back and forth where they could say, well, if you were on the sun and looking at it and you could view what the observer on Earth was seeing, you would see the 30 kilometer a second fringe pattern in the rest frame of the sun looking at the Earth. But since we're in an Earth frame, we actually can't measure it because we're going to be in the center of our own, we're going to be in the center of our wavefront, which would create a sphere, which means no change, no velocity change, rather than that ellipse form that we looked at earlier. So they come up with this like backwards interpretation of how to do all this. But this part specifically is in regards to velocity composition, which he will later turn around and say that if you drop his relativistic term, which basically means that you can't have any a speed exceed the speed of light, which is just done through this adding this denominator down here, where you just basically it renormalizes the velocity so that it can't exceed the speed of light when you do velocity addition with this one right here. So when he says, okay, this means that the speed of light can't be exceeded. Okay, cool. And if we drop this term, we can fall back to what Fizeau measured. So dropping this term that hard caps the speed, we can actually measure c plus or minus v. And this is somehow a confirmation of how uh, that he's on the right track here. So this is just for the change in velocity addition. And this is extremely significant because previously when you were doing velocity addition and things like that, what you can do is called the law of parallelograms. And what this shows is that in kinematics, relative motion is always true. So if relative motion is always true, if we describe here in the black line would be classic physics, you know, uh, what you would get by just adding velocities together. And then, so like, if you're on a train, you shoot a bullet, the speed of the bullet is the speed of the train plus the speed of the bullet. In relativity, they would say that, you shoot the bullet and it's independent of the speed of the train and it's just the speed of the bullet. So to satisfy this, and then we could look at it from a different frame and do the reverse because relative motion would always be true. So to complete this, what we have is the time and distance axis here. And then if we flip it for the relative motion, this would complete a nice little parallelogram here. And then what you'll notice is that the relativistic one noted in the dotted lines here makes a hyperbola. So it doesn't complete the angle relationship necessary to complete a parallelogram. So this is what this represents. In terms of the law of parallelograms, it becomes a hyperbolic parallelogram, but we can see that it is satisfied with the symmetry there. So this new hyperbolic version of the change in distance and time is being substantiated here with this math. This is what this math is representing over here when he goes into velocity composition and talks about all this. This is what he's substantiating. Okay. And then if you're in good agreement with kinematics, then you're good to proceed on to dynamics. So that's what he was putting forward there. Now, what this implies is that the speed of light is constant and independent of your motion. He later goes on to describe in his paper how you can apply his equations to any frame in uniform motion, even if, and regardless of its shape. So, if it makes a continuous curve, otherwise known as a circle, or any polygonal shape that's in uniform rotation, it should be, the speed of light should be the same. Because what you would do, like on this apparatus here from Sagnac in 1913, what we have is a turntable. We have a light source and a detector. So remember, there's no ether for this to be relative to in the current paradigm in 1913 when Sagnac did this experiment. So the relativistic interpretation of this experiment would be doing a Lorentz transformation between the detector and the source emitter here, because these are the two things that are, in relative motion to one another. Although when you turn this turntable, there's no relative motion between them because they're the same. In other words, the distance is fixed. But what's actually measured here is that the speed of light clockwise and counterclockwise, going with and against the rotation, is when the beam recombines, it's out of phase proportional to the angular velocity or the rotation rate of this apparatus. So the path length is preserved, and they can, in both directions, which leads to a change in distance over time, which allows for that beam to have a phase separation in it. Now we get into different relativistic explanations trying to explain this. We'll cover those in a second. But in principle here, what this means is that, or how Sagnac interpreted it, is that there was an optical vortex of ether created by the rotation of this apparatus. And that's what that's how the measurement with respect to that is how you get the asymmetry for there to be a fringe pattern. Because if the speed of light is independent of the motion of the detector and the emitter here, and and then it would, that would lead to the spherical wave fronts that the Lorentz transformation would facilitate, then these two beams should recombine with no phase change. They should still be in phase, but they weren't. And what we're looking at here is the old formalism that was used to describe the ratio of the fringes. They weren't able to measure the frequency change with electronic gear or whatever. So this is just the ratio of the fringes multiplied by the rotation rate, the distance of the apparatus. This is the amount of coils that were turned or basically just describes the geometry of the rotation going clockwise and counterclockwise. Sorry. And then we have N here. That's just the distance. S is the angular rotation rate. And then over the wavelength and the frequency here. So the modern formalism of this, you can reduce this down to the more familiar known, which would be 4 pi times the distance times the angular velocity over the wavelength. So this is, these are all equivalent. They're just written differently to describe the same thing. All right, so the travel time difference between them is delta t equals 4 times the distance, the area of this apparatus, or the linear version would be 2 times the length so just the length that it has to travel. And then instead of the angular velocity, it would just be v for regular velocity over c squared. And what we have is a linear configuration from Wang in 2004. So this right here on the face of it falsifies relativity theory and where the equations apply, because there's actually no relativistic derivation for the Sagnac effect that doesn't use a transformation to the center of the device to introduce a fictitious observer that remains stationary here to create the asymmetry for the clockwise and counterclockwise beams to be relative to, so that they can produce the first order fringe that's described by this equation here. And in Einstein's 1905 paper, in the first page, the big thing that he describes is that his theory is going to be independent of fictitious frames and luminiferous ether frames, and they're not going to be required. And it's always going to be about the relative motion between this detector and this emitter. So your detector is going to be your observer, your emitter is going to be your other observer, and the relative motion between them is going to be described by Lorentz transformation. But you will never in your searches find a derivation of the an analysis using a Lorentz transformation with respect to the detector. It's all what they'll do is they'll invoke a cylindrical coordinate, and then they'll overlay it on top of this, and then they'll have an observer in the center. They'll make the detector's motion around the center relative to that midpoint, and that's preserving the path length change for them so that they can have the timing difference. That's the only way to answer this. And then also, so keep in mind, this is in rotation. So, some people said, actually, Einstein never even commented on this. It had to be later derived by Paul Langevin, who said that, what did he say? That dude said that this falls under general relativity because it's a rotation. So he used cylindrical coordinates derived from general relativity, and then did the timing difference that way. But literally the same thing that I just described, but he tried to make it a gravitational effect rather than because it's rotation and an acceleration. Acceleration is equivalent to gravitation, so that's where they were going with it. But anyway, they end up dropping that kind of stuff, and then they just do the classic cylindrical transformation using regular Cartesian coordinates in flat space-time, because even though they started with general relativity for the which is curved space-time for the derivation for this, the infinitesimal slice that they break out is just flat space-time. So anyway, otherwise it would produce a different result, and it would be in a disagreement with experimental result. We can't have that. So they get curved space-time just flat enough to describe the regular flat space-time that's used for special relativity. But kind of digressed a little bit there. But in 2004, we have a linear configuration here that was done in several configurations. So the one that we're looking at here is the conveyor belt config, where the fiber detector is on a conveyor. And then this wheel, how they derive it with the math is they use the delta L. Now the delta L is going to be only the segment that's moving rather than the entire device, because what people will try to say is that, oh, it's relative to the detector, it's relative motion to the detector, and that's totally allowed, etc. It's like, if that's totally allowed, then just ether frame, what would be the difference? But anyway, this delta L here shows that it's only relative to this segment itself. So the V over C relationship comes out to be, this motion with respect to the speed of light, which is not supposed to be something that is derivable in relativity theory, because this comes out to be a first order fringe pattern in uniform rectilinear motion, which is the same kind of motion that they say the Earth is partaking in, and that's why we can't measure it, and because of link contraction and time dilation in that direction of motion. But here we have it being measured, and then we get into, well, we're not moving at relativistic speeds, this is moving much slower than that. Well, as you'll find out when you look at Mana Stone's video, you only start to see relativistic effects when you're at 10% of the speed of light. So the Earth traveling at 30 kilometers a second, if you if you just round the speed of light up to 300 kilometers a second, comes out to 0.1%. So we would have to be moving 300,000 kilometers a second. No, we would have to be moving 30,000 kilometers a second for it to be 10% of the speed of light, for there to be any sort of link contraction that we would, ever notice or whatever. And so if you're not moving at least 30,000 kilometers a second, then you fall back to classic physics. You fall back to Newtonian, velocity composition rather than relativistic, etc. So it just so happens that when you start to move faster, you somehow lose the ability to measure your linear velocity. even though it's not even in the confines of moving at relativistic speeds for heliocentrism for it to be applicable to apply a Lorentz transformation to a Michelson-Morley apparatus. So what we're experiencing here is that the ratio of V over C always is always in play, and it's the dynamic cause of the fringe pattern. Kinematics, link contraction, time dilation, etc., don't cause fringe patterns. They would actually predict no fringe pattern. So the only way that there could be a fringe pattern is if there's a change in the speed of light proportional to the velocities going with and against the medium to produce that fringe. So in other words, C, because the way that they teach it now is that C plus or minus V is a classic kinematic prediction, but that's low-key retarded because it produces a physical fringe. That's a real effect. That's a real measurable dynamic effect. And then they have to answer this in the relativistic means by doing a transformation to a fictitious frame to produce that same first order effect that they say can't exist, and then also using a frame that they say not only doesn't exist in reality, doesn't have any mathematical bearing on my theory, because my theory is different than the ether theory. And that's an extremely important distinction to have, because the mathematical formalism for relativity theory is 100% identical to the Voigt transformation. It's 100%, the half gamma order term is 100% identical to what Lamar derived for his theory, describing how the wavelengths, how the timing and spacing of waves would change with respect to the elastic medium due to relative motion in it. Now, in the 1930s, we have one of the most, what I would consider one of the most substantial proofs of relativity theory in terms of confirming their half-order gamma term, because if you're not familiar with the history of ether theories, you might be led to believe that there was no half gamma order term prediction, and that this half order gamma term is unique to relativity theory because it represents time dilation irrespective of any medium, and it's just due to the relative motion. Which again, if you're looking at it from the one way, if it's not reciprocal, then we could swoop it up as being just relative to the ether frame. But that's kind of we'll come back to that in a second. But this is the experimental setup here. We have a cathode ray tube that's going to emit hydrogen at a certain energy level, hydrogen 2, and then also hydrogen 3. And in this chamber here, it gets, they deionize it so it has no charge, and then they send it through an electric field so it increases velocity based on its charge through it. And then once it gets through that, they reionize it, and the reionization of it emits photons. In other words, it emits light. So that light is either going to go forward, or it's going to go backwards, hit a plate, and then reflect forwards to a detector. So in this manner, they can measure directly blue shift and red shift based on whether or not the light came directly towards the detector, or if it had to hit that mirror first and then bounce back. So now they have what they would consider a source. So they have this hydrogen atom moving at comes out to be like 800,000 kilometers a second or something like that. So they have the desired relativistic speeds that they would need for the detector and emitter, because no physical you can't have a flashlight or a laser moving at those speeds and admitting we can't test for that, it's too fast. So using this mechanism of the interaction created by reionizing the hydrogen to as a light source emitter, it's pretty ingenious, pretty cool. But this gives the desired speeds to test that half-order gamma term in a meaningful way. And this was supposed to be a test of the transverse Doppler shift. And if we recall earlier to how I was explaining that the classic theory would predict that there's no transverse Doppler shift because there's no distance change when you're at that symmetrical midpoint where it's intersecting you at 90 degrees. So you would get a spherical wavefront from that. And what I have found is that it's basically impossible using this setup anyway to measure the transverse effect, because the light goes in different directions and getting it directly on that 90 is just not tenable. So they measured the relativistic, so-called relativistic Doppler shift for red and blue shift. So this is what the apparatus looks like on the inside here. We're looking at the end of the chamber here, where they've reionized the hydrogen that's going through the chamber, and then now it's starting to emit light, and that light is either going to continue forward to the spectrograph, or it's going to hit this mirror here and then go back to the spectrograph. Now this is a truncated version of the setup. There was actually an angled mirror here at, I think, 7 degrees, I want to say, and then that would take you to the detector offsite here. But this is essentially what we're looking at here. And then here's just another visual of that, so we can see that the hydrogen atom here, it's been reionized, it's now emitting light. This is going to be blue shifted. It's going directly towards the spectrograph, which is going to look at the frequency of light there to look for the red and blue shift. And we have the red shift here hitting the light, or hitting the mirror, reflecting back. Same concept that we just went over. Let me make sure I covered everything I need to. I think that's about it. Here's another one for good measure, just showing the other side now of the chamber that it goes through, and then there's the electric field and all that to give it the acceleration and all that. And then here's another setup. Oh, here's the full setup of the mirror and all that, and the grading. So with that, we have we're just looking at eye candy at this point. Basically, I've already described the good points. So what he found here is down to the angstrom wavelength, which is an extremely small wavelength. They get down. What he shows is that there is a linear relationship in the velocity change there for the wavelengths to the tune of that half-order gamma term. And keep in mind, his test, or the way that he framed it in his paper at least, was that he was testing for Lamar's theory on that half-order gamma term that we talked about, where irrespective of the motion, there's still going to be some retardation in the frequency and wavelength, but it's just going to be a really small term. But and then at the velocities that we deal with, we're never going to really be able to distinguish that term, or that difference, because it's going to be overshadowed by the bigger first order result. But here he's testing it at so-called relativistic, at the appropriate so-called relativistic speeds, and then this change in wavelength came out to be exactly the half-order gamma term. Now, something I found during my research of this is that he actually used the gamma for the change in the mass of the hydrogen as it goes through the electric field, and that kind of creates a circularity here in the analysis where it's actually just a full V over C instead of a half, but because it was split from the change in the mass to the change in the frequency, in the measured frequency there might be some circularity there. So that's that was an interesting point that was brought up that I read. So that's kind of cool there. But yeah, same framework, confirming a different theory. That was his conclusion. And then it was determined that because the equations are the same and there's no ether and whatnot, they were like, oh, this actually confirms relativistic time dilation. But again, this is a one-way measurement without reciprocity between frames, source and detector, or two observers, A and B, for example. There's no reciprocity. So this is just a one-way measurement with respect to an elastic medium. Using the V over C ratio, because what this comes out to, what the V over C ratio comes out to, is C plus or minus V. Always. And always and forever, as they say. And then, of course, we have Dayton Miller, who continued. Now we're going to move on to another interferometer experiment, where earlier when we looked at the Michelson-Morley experiment, we saw that there was a bias in the east-west directions that was swooped up as experimental error, null result, link contraction, no real mechanism for the contraction. So keep in mind, at least Lorentz proposed, based on the change in the wavelengths of the electron, that there was going to be, that could possibly lead to the contraction of material matter. In relativity, in modern day now, there's no mechanism for it. It's just it just contracts. And then some people will even say, well, it's an apparent contraction, it's not real, yada, yada. And there's massive problems with that. And even citations of Einstein clearing up that paradox. I forget the year, I want to say 1926, maybe. He wrote explaining how, if you would measure that changed rod in time if you were in the rest frame. So you would basically see that observer having that changed wavelength. So in other words, confirming that it has to be a real effect. And if it's not a real effect, if it's not dynamic, then like it has no physical meaning anyway. But anyway, Dayton Miller did a series of interferometer readings. I want to say he did like 5 million or something like that. Can't remember off the top of my head. It's been a while. But all of his readings span over the course of 30 years. And what he found is that there is a sidereal and annual solar periodicity measured. But again, it is not to the tune of the 30 kilometers a second. And he also found that it changes in altitude as well to the square of the height above sea level. So this would directly refute, relativity on the face of it, because we have a speed of light that's not isotropic; it's directional dependent. But it's just not to the tune of what they would need. So they would have to come up with an entirely different theory to describe, physics and their explanation for how they can keep the Earth in motion. And then this data was heavily suppressed, ignored, etc. And then a final review was done about 16 years or 14 years after Miller died by his former lab assistant, Robert Shankland, who basically did one of the most egregious hit pieces ever known to man. And we actually just did a reading night recently on Ether Cause of Shankland's paper, and Stone did a phenomenal breakdown of the analysis and how the data was butchered to make it appear as if the signal was not physically meaningless. So like the TLDR from the paper is that they don't dispute that there was a fringe shift measured. They just say that it's not physically meaningful. They tried to say that it was due to temperature fluctuations and all that. But as you read through the paper, they actually drop that claim at the end and have no tenable explanation for it. And it's rather dissatisfactory in terms of an explanation. And then later we're left in I think it was like 2020, 2022, maybe, a guy named Thomas Roberts did a paper where he did a Fourier analysis where he set the error bar to the exact amount of the periodicity measured under the Fourier transformation, removed the periodicity that was set for the error bar, and then concluded that there was no, that it was physically meaningless. And it's like, none of these people are disputing the actual fact that the speed of light measured differently in the east and west directions to create this fringe pattern, to create this magnitude. When you plot the minimum and maximum speeds throughout the day against sidereal time, you get a sine wave. None of them dispute that. They just say it's physically meaningless. And Roberts ends up concluding that the measurements are due to systemic error, a systemic error that is present in 3 different interferometers in different locations all over the world, in different altitudes and in different environments. One is in a basement below sea level. The other one is at sea level, or 200 meters above, 200 meters above sea level. And then the other one was at Mount Wilson, which was, I want to say, 1,800 meters above sea level. And the environment for that was basically the guy made like a shack made out of hay, because what he ended up finding out through his different experiments is that the shielding that you use for the interferometer affects the readings. So there's what he, or what you can conclude from that is that like the ether moving through a material medium gets, that affects that periodicity in the fringes there. It's still present, but like the amplitude will go down. And that was something that Demjanov found in the later experiments that he did, but based on the refractive indexes and all that. So basically the shielding affects things. If it's in a basement, concrete and steel walls, you're going to get different readings and stuff. And so to get the best fringe readings, you need an open flow, open area, and you need, not metallic chamber, non-metallic chambers, and all that kind of stuff to get the best results. And then in modern times, what they'll do is they'll do these experiments in the deepest, darkest basement they can find in a vacuum, with the hardest material shieldings, etc., for all of this. And what that produces is it reduces the amplitude of the sidereal fluctuations there, and then they conclude that, oh well, the speed of light must be constant because we've reduced out the variance and the east-west bias when, as Dan Geminov showed, it's still present. It's just the amplitude is reduced significantly. So, and again, so we have some repetition of Miller's work, and that was done by Hector Manera in 1998 to 2004. They left their interferometer running for 3 years straight and took a series of, just basically took that total data of 3 years and plotted the min-max dimensions against sidereal time. Again, found the same exact relationship as Miller did. And then there was also Yuri Galev, who did some radio interferometry and optical interferometry and found the same sidereal fluctuations. And now perhaps you're not convinced that these right angle interferometers measure an east-west bias. Maybe these are all wrong. These people were lying. Maybe there's a systemic error. Okay, cool. That's possible. But if we add another right angle to the interferometer, and instead of having it make a cross, it makes a closed loop, like a rectangle, all of a sudden we say that, oh, we're measuring Earth rotation. Well, how do you measure Earth rotation? Well, there has to be a bias in the east-west directions of the speed of light. So somehow, miraculously, adding another right angle turns this into, oh, yeah, sorry, there's an additional thing you have to do. So earlier we talked about how you can get the velocity component by squaring the distance of the fringe in that proportional ratio. So for the angular velocity, because they want it to be looked at in terms of a rotation, they don't want to put a velocity to it. They just want to put it as a rotation rate that corresponds to 15 degrees per hour. What they'll do, instead of squaring the distance to the fringes to get a velocity, which as Sagnac, Jones, and everyone showed is possible for rotation, what they do is they just plot the minimum, maximum dimensions for the fluctuations in the speed of light throughout the day, and then they plot that against sidereal time instead of getting the velocity component for it, and they just go, look, this is how angular velocity is produced. This measures angular rotation. So something like Michelson, Gale, Pearson, that kind of rectangle closed loop interferometer, a ring laser gyro. You can look it up now. It's called the Ginger Project. It's called the General Relativity in Underground Gyroscopes or something like that. It's some big project like that where they're all claiming to measure, sidereal rotation. One even claims to measure the periodicity of the moon, etc. But all they're doing, right, is they're just plotting the min-maximum dimensions of the speed of light throughout the day against the timeline. So in this, it happens to be sidereal time, which is 23 hours, 56 minutes. And that makes the sine wave. When you plot it against 24 hours, it makes nothing. It makes incoherency. And I'm guessing to get the notation for the moon situation, they would be plotting it against lunar time to get that for the periodicity. So it's really interesting that there seems to be a periodicity that fluctuates with respect to sidereal time and solar motion and apparently lunar motion, but not to the tune of any velocity that is acceptable to confirm heliocentrism, in the sense that Kepler's equations and Newton's equations correctly describe kinematically and dynamically the motion of Earth through space around the sun. And that is the end of the presentation. If there are any questions, comments, or concerns, you guys are super open to those. Well, don't all start asking questions at once, lads.
I think you stumped them.
Yeah, I was just wondering, how long is it going to take for most of the people to go through the paradigm shift rather than making excuses as to why the silence isn't silencing for them?
Well, almost never. I've been on a 5-day debate now on Twitter with a physicist from CERN arguing relativity and the equivalence of the Voigt transformation, etc. It's gone nowhere fast, just deflection and gaslighting. No actual answer, just claiming that, both observers A and B would measure a spherical wavefront. Relativity is true, just nonsense. So it's going to be a hot minute because people have, we're taught like that all this is correct before we have a chance to like critically think about it. And then on top of that, when you move up in academia, you actually get rewarded for completing the calculations and not really necessarily having the physical interpretation. Because a big part of the conversation that I'm having with dude on Twitter is that, you know, the mainstream physics labs, they don't care about the physical interpretation. They just care that the math works. You know, they have the math is reality mindset, and they don't care about the physical interpretation of what they're calculating. Because, like I was saying, the equations for relativity and the elastic ether theory for the transformations are identical. There's no difference. So the thing that would substantiate relativity would be a basically you would have to have your stationary clock and a moving clock, and the moving clock would retard as a portion of its velocity, and then you would somehow have to have that stationary clock be, you know, it would have to experience a shift proportional to that velocity of the moving clock, and that's never once been measured. That's, you know, reciprocity is demanded in that theory, and it's never been measured, never present. So every experiment where they're like, oh, how about at the CERN collider, and we're measuring the time dilation of a muon because it's able to traverse this distance and its half-life is only 2.2 nanoseconds, you know, that must mean it was dilated. And it's like, okay, well, if it's dilated and there's reciprocity and transformation, then there would have to be dilation and link contraction in the lab frame, but not a single physicist on Earth has ever argued that the Large Hadron Collider is contracted and dilated relative to the stationary muon. So it's always one way. So in other words, another way to interpret this, anytime they talk about dilation like that, what's happening is the speed of light is either being retarded, or it's going superluminal. It's traveling faster than the accepted value. And the only way for them to conceptualize this is that time slowed down and lengths changed, but the same distance was traversed because of the constancy. So this is how they turned length contraction and time dilation, which is really c plus or minus v, into a change in the coordinates describing time and length. So instead of getting c plus or minus v now, you get a change in time and a change in length directly proportional to that velocity that produced it. And there's nowhere for them to really go in that paradigm, Larry, because they're so committed to this, and then they built upon it with general relativity, which has to be backwards compatible with that through equivalence principle, through flat space-time, etc. And so there's really no way to go back. And then they've come up with cosmological models based off of solving, you know, the general relativity equations, so that there's nowhere for them to go. They can't teach anything new because there's only two paradigms here. There's absolute time and space, which is facilitated by an ether theory, and there's no absolute time and space, which is facilitated by relativistic physics.
Well, you mentioned that nobody says that the stationary muon sees a dilated, shrunken CERN. That actually is the prediction of relativity. That's the whole point, is that each one sees the other one shrunken and slowed down and so forth.
So you would need direct measurements of the change in length of the apparatus. Like, that's never present. It is a mathematical prediction for the symmetry. It's never once been measured.
Well, because you can't get a measurement device up to near the speed of light where you'd have a meaningful difference.
Well,
you're always doing the measurement in a specific frame of reference, and the measurements are all relative to that frame of reference, right?
Sure. And if that's the case, then these can be all swooped up under the same framework that shows the asymmetry as a feature and not a bug. In other words, what you're saying is that there's no experiment that's been able to differentiate between relativity and the ether theory, which is my premise.
That was actually what I was about to ask you, is do you have any prediction differences between relativity and your ether theory? Because from the sounds of it, you're basically just saying that they boil down to about the same thing, at which point you're basically just doing Einstein, but with a different mental model of it. And wrong with
S-
that, but it doesn't
s-
mean
a-
much.
Absolutely. So for certain experiments, it's indistinguishable. Like for example, the muon, like you pointed out, and that's actually where I took the conversation with with the gentleman I was talking to on Twitter. We would have to move to interferometry predictions, and that's where we get into Sagnac and Wang. When you get into the relativistic derivation for the Sagnac effect, there isn't one. They have to use a preferred frame. It's completely unanswerable. I've done prezzies where they're actually I have to pull it up. There's about 25 different derivations of them trying to explain the Sagnac effect, and each and every single one of them violates the principles of relativity, and they use that ether frame uh, to answer it. They can never do it between source and detector because they predict that there's no relative motion between them, and that they should measure the speed of light being the same in their frame. So if the detector frame can't measure a difference in the speed of light, it should measure a fringe that's um, or it should measure no fringe actually. And this actually created a huge problem in the Michelson-Gale-Pearson experiment because they're measuring an east-west bias in the speed of light to create the fringe, but they're in the lab frame. They're in the frame that's in motion. So like they shouldn't see a fringe. They shouldn't be able to measure it. So what they do is they'll say, okay, we need to transform to the center of the ECI, right? They do a transformation to the center of the Earth, which is essentially moving an observer to the center of the Earth, and then you're looking out at the detector at the rim of at the at the outer rim of Earth, and then it's in rotation relative to you, and then that's allowing you to measure the distance change. But that's physically retarded because we're in the moving frame. We're not at the center of the Earth. It's only a mathematical construct that has to obviously violate the principles of the theory to even try and explain it. So like our predictions for interferometry and Sagnac and stuff, that V over C relationship to create the physical fringe, that is the differentiating factor between the two theories there. And then in the other cases where it's a one-way measurement, like the muon, and a couple other examples like time dilation, et cetera, for moving clocks in either space vehicles or Heffel and Keating, et cetera. Those are all one ways. So those, there's no contradiction in our theory there. It's completely equivalent. And it's actually just the V over C Sagnac effect. So get this, if you get into satellites, they say that a satellite is in an inertial frame because it's in free fall. Under general relativity, free fall constitutes as an inertial frame. So there should be no change in the clock speed on a satellite or space vehicle, otherwise known as. And what they actually have to correct to keep the clock in line is Sagnac corrections. So they say that, oh, the clock is losing time with respect to the center of the ECI. It's crazy.
Well, I mean, that actually makes a lot of sense. Like different reference frames can do different things relative to each other. They're like, even if it's an inertial frame in its own right, that doesn't mean it has the same. Like, sorry, I'm wondering if I'm misunderstanding your argument or you're misunderstanding relativity. Um, but yeah, like each inertial reference frame can have time running at a different rate relative to another inertial reference frame under
Yeah,
special relativity. That's
yeah, but do
that's
you
the whole
under
point.
No. So, well, you're half correct, but there has to be reciprocity between the frames. So there has to be some clock on Earth that experiences a time shift proportional to the velocity of the satellite. Otherwise, there's no reciprocity. So this is the whole issue in it. And if all inertial frames are equivalent and equal, which is defined here, right here in Einstein's paper in 1905 as a basic premise, then that clock has to retard on Earth proportional to the velocity of some other thing. When they're making it proportional to, I'm sorry, when they're making it relative to the center of the ECI, there's no clock at the center of the ECI. There's nothing at the center of the ECI. There's no other thing there. So they're making it relative to a literal preferred frame. So I'm going to read a little bit from this first page because this highly illustrates the contradiction here. So we have, let's see, examples of this sort with the unsuccessful attempts to discover motion of the Earth relative to the light medium suggest that the phenomenon of electrodynamics, as well as the mechanics process, possess no properties corresponding to the idea of absolute rest, meaning that there's no light frame for it to be relative to, there's no fictitious frame to do a V over C2 or anything like that. It has to be relative to this other observer, and you have to use a Lorentz transformation, and which is going to constitute a change in time and distance. They suggest rather that has already been shown to the first order of small quantities that the same laws of electrodynamics and optics are valid for all frames of reference for which the equations of mechanics hold good. So if you are in an inertial frame, you are measuring the speed of light as a constant. You are not measuring it different relative to anything. It is always constant for you, no matter what, if you are in an inertial frame. We raise the conjecture, the purport, which will hereafter be called the principle of relativity, to the status of a postulate. So real quick on the significance of changing a conjecture to a postulate is nothing. And we will introduce another postulate, which is apparently irreconcilable from the former, namely that the speed of light is always propagated in empty space with a definite velocity which is independent of the state of motion of the emitting body. So, and what isn't said here, but what is implied in what this whole paper is about, is it's also independent of the state of the motion of the detector, because all these transformations and all of this is between two observers, etc. And if it's not, and if the speed of light is dependent on those, then he's not saying anything different about physics that was already established. So this has to be, he's laying the groundwork here for making the transformations relative to another observer, rather than the light medium in which the original Voigt transformation was derived under. So these two postulates, now this is the important part, these two postulates suffice for the attainment of a simple, consistent theory of electrodynamics of moving bodies, based on Maxwell's theory for stationary bodies. The introduction of a luminiferous ether, being a physical medium, will prove to be superfluous, inasmuch as the view to be developed here will not require an absolutely stationary space. So they're not going to put an ECI into a measurement where there isn't one. It's always going to be relative to some other clock that's in motion, some other thing that's in actual motion. No arbitrary rest frames. Oops. Which will be provided.
Can you remind me what ECI stands for?
Earth-centered inertial. So it's just a coordinate system that describes.
Yeah.
Yep.
Sorry.
Gotcha. No, you're good. No problem.
Misunderstood for them. No, that is it.
Nope, you're good. It's just a fancy way of saying at the center of the Earth. Provided with special properties, nor will it assign a velocity vector to a point in empty space in which electromagnetic processes take place. Now, the only way that they could answer the Sagnac effect, which I'll show you guys right here, is where's Ether Critiques? Ether Critiques, we have Tartaglia. Yes, right here. 5. And then, so they start out this paper trying to explain the Wang experiment that we went over earlier, and how this could be a relativistic effect, and how it's all good and gravy. So they start off by saying that, the classic kinematic treatment of C plus or minus V is valid, but we're not going to do that here. We're going to show you the relativistic treatment here, which is the dynamic one, I guess. Even though the classic one isn't kinematics, it produces a fringe. It's a real thing, so it's dynamic. Anyway, so they go on to give their derivation for the classic here, and they end up with the delta T is approximately equal to 4 times the area times the angular frequency over the speed of light squared, which gives them their fringes. All right. And then they say, however, that said, the Sagnac effect does not need any ether at all. Oh, no way. You're going to derive it under relativity using just geometry. Okay, cool. How are you going to do that? All right, well, we got this cylinder here with a slanted timeline. What does that mean? Well, let's unfold what they do here. They create a cylindrical coordinate system, put it in the center of the device, make the deviation measured by the detector relative to the midpoint established by the fictitious observer in the center of this coordinate system, thereby contradicting themselves right on the face of it, because this is this. Provided with special properties, nor assign a velocity vector to a point in empty space in which electromagnetic processes take place. There is no detector in the center of this device, mathematically, or in reality. This had to be invoked as a fictitious spot for the comparison, so that they could assign velocity vectors to electromagnetic processes in the clockwise and counterclockwise directions to create this deviation in the timeline. And then they go on to do some.
It just seems like a mathematical convenience, not anything like really critical here.
The introduction of a luminiferous ether will prove superfluous, inasmuch here as the theory to be developed will not require an absolutely stationary frame or anything of convenience provided with special properties, nor will it assign a velocity vector to a point in empty space in which electromagnetic processes take place. Now, it's possible that this is a frame of convenience just for ease. However, it's not. I've been through 20 plus derivations of the relativistic Sagnac effect, and it cannot be done without invoking a fictitious frame to make the motion relative to. And we'll go over some more of those in a second. We can bang out a bunch of them, but I wanted to show the Tartaglia one specifically because they say that this is the treatment for how they're going to explain the Sagnac effect in the linear motion of Wang's experiment. What we're looking at here is a symmetrical midpoint arbitrarily defined for the motion to be relative to going left and right to create the fringe pattern. So this is absolutely exactly what Einstein was saying that his theory is not about, because this theory, doing this, is the ether theory. This is an asymmetry. This is making the motion relative to, this fictitious point, a rest frame that isn't there. Einstein says no, should not be that way. And keep in mind, for this configuration, the way that they do the transformation, regardless of the analysis being in the parallelogram configuration, which is what they're doing here, or the conveyor configuration, where the detector is co-moving along the conveyor, there should be no relative motion between them, yet they have to invoke a completely separate symmetrical midpoint, which is absolutely not of convenience. It's mandatory to get the fringe pattern, because otherwise the speed of light completes the circuit in clockwise and counterclockwise and produces no fringe. And then they conclude here that if they do, if they expand out the higher order gamma term, that it will eventually lead to a not higher order term of the 2 times the length times the velocity over c squared, which is completely preposterous. All right. I'll pull up some more Sagnacs real quick, and we could take a look at those. Some of the other derivations and go over what they're doing here. But yeah, mathematical conveniences are tricky because the way that it's framed, it's like, oh, it's just for convenience. And you're not the first person to suggest that. That's like, I actually went back and forth with Blitz on this, and we'll look at his derivation, what he had to conveniently do to describe the effect, and there's no way around it. Where's my hold on a second. Projects, presentations, relativity, how Sagnac. There we go. Okay. So this is a really good citation. I highly recommend you guys check this one out, because it gives about 25 different ways that they try to derive the Sagnac effect. And then you can look at, their math and stuff and what they did. And you can see that's actually what I did. That's what this whole Prezi was. It's pulling some of those out and looking at them. So here we're looking at, this is from Generalized Formula Review for Wang. I think this is the one where did they do, this isn't GR. It's been a while since I've read this one, but they end up doing the exact same thing in here. But more specifically, we're looking at the Wang one, the Tartaglia one. Here they try to use general relativity. They take a flat space-time metric, and then they say, they make it relative to the midpoint again, do an integral of the device with respect to the midpoint, and then just, oh, look, there's your fringe. And then we have same thing again. Well, that was from Tartaglia, that one. We have okay, so this is Paul Langevin in 1937. Now, in 1918, he actually proposed, this solution as how to describe the Sagnac effect in terms of relativity theory. But oh, dude, and that leads us to Dufour and Prunet. Somebody remind me before we can, or after this, to go over Dufour and Prunet, because that's a really good one. But anyway, to answer Dufour and Prunet's experiment, which is just another Sagnac configuration, which we'll go into the details in a minute, he basically describes this as a coordinate system rotation, and he uses central time, which is just lab time, and he puts that in the coordinate for the fictitious observer so that it's compatible with the actual measured experiment. But all this fancy math leads to, even though it's derived from general relativity here for the coordinates, it describes a directionally dependent speed of light, and it also implies absolute time, because he had to use lab time to put in for the ether frame that he invoked. And then he does another one where he tries to like warp time around the central axis of it, and it's just, none of these are physically provide an explanation. And then Blitz tried to do a similar thing where where it's a coordinate system rotation relative to a midpoint, which is just, again, a directionally dependent speed of light, is completely antithetical to an isotropic speed of light where there's not a ether frame for the motion to be relative to, et cetera, et cetera. Their theory actually predicts no fringe pattern, and we could look at what that means here in a second. Okay, we'll take a look at, where is Engelhardt? No, that's not it. It's yeah, here we go. All right, so the classic and relativistic derivation of the Sagnac effect. So under the principles of a frame for the motion to be relative to, he derives the clockwise and counterclockwise change in the speed of light, and there's a leftover higher order term here, which comes out to be canceled out because it's too small to be measured, so that you just drop this term out. And what we're left with is the speed of light is different going clockwise versus counterclockwise. And this can be reduced to the formalism that we were looking at earlier, which is the change in time, or the change in the fringe pattern produced, in other words, is proportional to 4 times the area times the angular velocity over the starting wavelength. And that's the classic Sagnac effect right there to produce your fringes. Now, when you get into the relativistic derivation, what we're left with here is, I don't have my highlighted one. Here we go. Okay, so remember, there's no midpoint for the motion to be relative to. Inertial observers measure the speed of light being constant in their frame, so there can't be a fringe. And then we have here the speed going the change in the speed of light going clockwise and counterclockwise, that timing difference is 0, comes out to be 0. If they're in an inertial frame and the speed of light is constant, then they measure no fringe. The Michelson-Gale-Pearson experiment in 1925 already showed that Voigt's postulate of C equals a constant is untenable. But remember, Voigt wasn't saying that the speed of light is a physical constant. It was purposely an asymmetrical transformation to show what the motion does relative to a light medium, or relative to the light medium rather. So, all right. And I think I can pull up one of Post saying it, because a lot of people are like, that's just your interpretation. You don't know what you're talking about, Alan. You're just some guy.
What paper was that you were just citing to? Sorry, I just want to look it up a little bit.
Oh yeah, no problem. I'll give it to you real quick. This is the Engelhardt. Putting it in the chat. Putting it in the chat now for you. Copy. All right. What were we talking about? Or where was I going to take it? Oh yeah, the Post guy. Let me see if I can find this real quick. Search. Let's do Post. Get close. Yes, here we go. So this is from Post EJ in 1967. If you're not familiar with him, he's a pretty well-known physicist. He's trying to give a explanation here to relativity theory. And he says, to be consistent with the principle of relativity, that the speed of light is constant in inertial frames, one has to demand that the Sagnac interferometer and the laser interferometer cannot lead to a fringe shift or a beat frequency if the equipment is in uniform translational motion. So remember that beat frequency is that measured change in frequency that's directly proportional to velocity. It's hugely significant there. And he's just kind of telling it like it is. Like he's not saying anything crazy or far fetched. It's just, I mean, we just read it from right from the horse's mouth. So it's just like it's maintaining that physical interpretation of what's being calculated and not violating the actual principles, because what's often overlooked is like, that was Blitz's and others' whole argument is that, it's just a frame of convenience. And it's like, well, show me one where it's not, where you can do it relative to the detector using a Lorentz transform. And you'll notice that there's no Lorentz transformations. Let's see. Canva. There's no Lorentz transformations in any of these. These are all Cartesian coordinates that, make it relative to a midpoint that's being invoked and then borrowing lab time, etc. So that there is no Lorentz transformation from detector to source to describe this because it predicts no change. So it's not convenience, it's mandatory.
So would the globe have to go stationary ether to fix this issue?
100%. That is exactly, if you ever came across the work of Dr. Robert Bennett, he is a globe lad geocentrist, and the ether is what facilitates the mechanism for all of this, because it's the only thing that makes physical sense to keep that paradigm, because the dynamics asserted that, for Newton, using big G and big M and little m and all that to describe the gravitational potential between the bodies and all that, to say that, the sun moves around the earth because of the gravitational potential and all that, was falsified by, there's no velocity component that's measurable. And then the only first order measurements that exist with interferometry don't have a velocity that corresponds to that. If you take them at what they are at first order, then the only interpretation you could have is that the objects in the sky and stuff are all moving relative to us. You got to go from there. But yeah, that is the direct implication. That's what it would be. Yes, sir.
Thank you, sir.
That was a very clarifying bit, man.
Yeah, thank you. If there's any questions or anything like that to further clarify, just let me know. It's like, yo, show me a Lorentz. I was like, show me a Lorentz transformation between detector and source that describes Sagnac. He was like, all right, here's what I'm going to do. I'm going to take Minkowski rotating cylindrical coordinates, put an observer at the center, make it relative to that radially outward for a directionally dependent speed. Like, dude, you missed the assignment. All right, so really quick recap. Relativity theory offers nothing unique or physically distinguishable from an ether theory, and there are experiments, especially in interferometry, that show that the non-reciprocal nature of light has to be invoked to describe experimental results rather than the constant speed leading to reciprocal transformations where the observer in his frame can't measure a difference. It's not what happens at all. And it's completely contradictory to Doppler shift and all that. But what they'll do is they'll say, oh, well, if you're not moving at relativistic speeds, you can just use classic Doppler. Oh, okay. Well, once you hit that, and then if you were like, well, what's the speed limit? What's the exact velocity where the beat frequency doesn't work anymore? Dude, that's such a good question. Okay. What velocity would produce no beat frequency change? Like which one specifically? There isn't one. It scales all the way to any velocity you enter. And then So what you'll see, like academically, I found a couple of sources that say that you need to be moving at 10% of the speed of light for relativity to kick in, etc. So there's just like this imaginary velocity where you're traveling so fast you just somehow can't measure it anymore.
I mean, no, it gets stronger as you get faster. Like normal kinetic energy, 1/2 mv squared, is, if you do the math in special relativity, that's E equals mc squared as applied to like Lorentz transformations and all that. It's mass increase as you go faster. The math is identical at low speeds. So you can do relativity at low speeds. It's just overcomplicated and unnecessary. But the 10% of the speed of light is a rule of thumb for certain applications. It's not a physical law or anything.
Well, it's not physically anything because the applications where you apply the scenarios where you're talking about, those are going to be one-way measurements that don't show reciprocity. And in the scenario where reciprocity is demanded, there isn't any. So, and like here's the thing, on top of the Sagnac stuff, there's a thing called a phase conjugate mirror. And a phase conjugate mirror is unique because what it does is it reflects the light wave back with the same, it preserves the wavefront. And what they've measured is that like it's essentially a one way, it's a way to like look at the one way speed of light. The wavefront is already changed before it hits the detector. It's already changed because if it was constant, then the wavefront that it reflects back would be preserved, right? And it wouldn't change. Like, so there's like, there's just nothing that gives agreement with relativity in the way that you're suggesting. And it's like, it doesn't matter how complicated it would be mathematically, it leads to a scenario that's C plus or minus V with respect to some frame that isn't permitted by the theory of relativity for it to be uniquely different from the old ether theories, because those ratios are all we just looked at them, they were all the same ratios from ether theories down to Lamore's for the half gamma, and then starting with Voigt for the actual transformation for a Lorentz transform. So
You asked us to remind you, and I just forgot the guy's name. What did you want us to remind you of?
Dufour and Prunet. So this is a really, really good one. And this one actually tripped up Paul Langevin. Let's see here. Because without invoking that fictitious frame, if you try to do source and detector, relativity is off by an order, by a magnitude of 10, I think it was. So we'll take a look at that. That be relativity. Again, nope. It's under optics, maybe? Nope. Ether. Here we go. Dufour and Prunet. These dudes were awesome. So Dufour and Prunet, 1942, redid the Sagnac experiments in their original configuration, and they were able to use pretty much all of the same parts that Sagnac used, I think, except for maybe the mirrors or something like that. I think one was cracked, so they had to use a different mirror or something. But they basically they reproduced Sagnac's, change in time is going to be 4 times the area times the angular velocity over the frequency, produces the fringe shift for the pattern here, for proportional to the velocity. So they were like, okay, cool, Sagnac confirmed. But what else can we do here? Let's see. Tell me I didn't put a. How did I do a Prezi on this and not show the configure? Oh, I did. It's right here. Okay, so now they also did an additional configuration where what we're looking at here is a light source emitter, and a detector that are fixed to the lab wall. So we have two things that are definitely not moving relative to one another, 100%. And then we have a turntable here that rotates. And then we have a stationary table here at the bottom. Actually, I think it's reversed. The top table stationary, the bottom table rotates. But anyway, this bottom table, they have 45-degree angled mirrors on it, so we can look at the path of light here. Now we'll look at the side view from it here. So we have light source detector on the wall. It's sending a signal. It hits the beam splitter. It hits 45-degree angled mirrors, and it goes down to this turntable that's rotating. and it completes a circuit here, hits 45-degree angled mirrors, and comes back up to the top, goes back to the lab wall. So the source emitter and the detector, there is absolutely no relative motion between them. The top part in here are separated by, I believe, 10 centimeters or something like that, off the top of my head. Not very high, but it was separated. And then, so what they measured was the proportional velocity of the rotation of this turntable. It measured an inertial detector and an inertial observer, source and detector fixed to the lab wall, measured a change in velocity and the speed of light as it traversed a circuit and rotation, meaning that the path length change was preserved with respect to some thing that isn't present here, that's preserving this in order for there to be a difference in the clockwise and counterclockwise speed to produce that fringe pattern, which is extremely significant here. And what we're looking at is the fringes produced from that. And what we see is a little slice in this fringe here. This is due to the Doppler shift from the mirrors, basically intersecting with the stationary mirror, like the motion relative to that created this little slice here. But the fringe pattern length, when you square that, it's proportional to the velocity or the angular rotation rate. Now, another key part of this is that if you try to do source and detector, relativity is approximately, they predict a fringe that's 10 times smaller, because remember, they don't predict first order effects, they predict second order v squared over c squared effects. So they actually can't predict the same physical amount if you were to apply, a Lorentz transformation to it. And Paul Langevin's argument was, well, we're dealing with rotation, and rotation and gravitation are equivalent. Therefore, you need to, and because gravitation pulls things inward centrally, we have to, the central frame is a frame of convenience, and that's the one that we should use. But that's like, again, contradictory. But the only possible explanation that they could use, otherwise they're going to be off by 10 times the amount. Thank you for reminding me of that, Larry.
You're welcome.
Let's see if we got any other gems in here. Just GPS doing Galilean transformations between the ECI and ECF, establishing absolute time. And then also the same for space vehicles, etc., all linked to the same time. Just, all right. But that's it. That's all I got so far.
So it's basically the old Freudian trope, gaslight, double down, gaslight, triple down, make excuses. I mean, it's just, it's tricks. They're just doing tricks, it looks like. They're trying to trick you back into accepting their explanation as if it's experimentation, and there's no, there's nothing to question here.
So
They're just like, take my explanation.
the big old appeal of possibility, man.
Yeah, and then so I'll link a thread here if you guys want to check it out for historical purposes and see kind of the back and forth and the gaslighting you get is unfortunately the state of mainstream physics when confronted with this. It's like you're basically told you can't know because you haven't been through 4 years of physics, you can't pass 8th grade math or what, like all kinds of like just basically your physical interpretation of what they're calculating can never be correct, even when quoting from Einstein directly himself, even when going through all the other experimentalists, even when going down the difference between the fringe pattern using a fictitious coordinate system, all this stuff. It's like there's no answer for it, and then it's just protected in the shell of like I'm a professor, I got paid to learn this, it can't be wrong. It doesn't matter if it physically makes no sense and is contradictory. It's what I was taught and then paid to teach. So that's kind of the mindset, and that's kind of where the argumentation goes. Anytime I try to bring up the equivalence or show how it's the same and where we differ and stuff, it just leads to gaslighting. I don't understand. It's like no explanation as to what the misunderstanding is, just I flat out don't understand, etc. So That's really all. That's really all. That keeps relativity and the Earth in motion. Is the lighting of the gas.
So anytime someone says that you don't understand, you should always reply, "You're right. Maybe I don't understand. Maybe you could explain it to me so I could understand." And that puts the burden of proof on them to back up their claim that you don't understand.
That
So
is,
I've been dealing with that for like 10 years.
yeah, no, that's extremely important to do, and I actually did that in the thread several times. Actually, I was like, "Yo, if any of this is word salad," because his response to the midpoint of the thread that I linked, where I was like, where I summarized his position, this other guy's position, and my position, and he basically said that that was word salad, and I was like, "So what part specifically was word salad? Because I'm here to help clarify." No response, nothing. Asked him 3 times. He just keeps asking other questions now, like doing the classic gish gallop, because it's just like no matter what, I can fundamentally never be right. So he never has to face it.
Well, I guess we should thank Freud for that. He's like the master of gaslighting. Um, it's unfortunate though. How come, we can't just have a conversation about it instead of accusing people of, well, you disagree with me, therefore you just don't understand. And we should take explanations over experimentation. And it's like they're constantly pushing this, you have to agree because, the earth goes around the sun. They need that motion of the earth. They're desperate for it. It's like anything else is like you're sabotaging their. If you don't agree with them, you're sabotaging their basic or their dogma. And science shouldn't be about dogma.
Yeah, agreed. Shout out to Tiny Ear in the chat who said, "Math and physics can't admit ether because their axioms assume invariance without a medium. Adding one breaks the self-consistent frame." Well said. That is exactly the issue at hand. They have to break their postulates to satisfy experimental measurement, which ruins their axioms about the invariance being relative to another observer and not a light medium. That is exactly the whole issue, dude. Well summarized, man.
Saying they want the mechanics, but not the actual thing.
They want the math to work and then to ignore how it works mechanically. And then they want to try and dress up the math as if it describes what's happening mechanically without violating their axioms. Dude, that guy crushed it. It's a great response. Who are you, Tiny Ear? You... All right. I think that's all I see here. All right. Well, if there's no further questions or any other experiments anyone wants to go over, I'm happy to go over them. But if there are none, I'm gonna close up shop here and see what the dinner situation is around here. I heard it was spaghetti night, allegedly.
Nah, that was a lie.
Oh, spaghetti is a lie. No. All right. That's fine. All right. Well, close out the stream here. Gio, thanks for hosting as always. Muchos gracias, senor. That's French for thank you.
Yeah, no problem. Cheers.
Yeah, dude. That's say no problem. Cheers. No, I'm just kidding. But yeah, bro. Who was that, Beast? You got is that soundboard? Is that soundboard
No,
or is that a
me.
live?
He just raw dogged it. That was awesome.
That's just in case you're away from your mic, got you back.
Yeah. Nice.
Awesome. All right. Well, we will
good stuff.
Yep. Thank you, sir. We will return Monday for this celestial theody. Took a little break, then came back, and then took another little break, but we are back now. So we're going to be going over that. And I think if I if I'm not mistaken, I believe Miss Coco and one other lucky Glober will be our participants for the Celestial Theodolite. We're going to be going over it from the ground up to see if we can cover the basic principles of anything we missed or anything that's not understood. We will clarify everything ad nauseum. So that'll be fun. Look forward to that on Tuesday. Or I'm sorry, Monday. And Sunday, we're going to be doing Glowbusters. Man of Stone's going to be doing his presentation on ether and how he thinks the ether and electricity and hopefully magnetism, how that works too. Because like magnet explanations are one of my favorite things.
Your hopes will be fulfilled.
Oh, nice, dude. I can't wait. So that'll be awesome. So tune into that at 3 p.m. Eastern. And then Tuesday will be Ether Roundtable. I think we're probably going to read a paper that night. We're going to be reading a superluminal paper that Piezo found recently that looks really good. So we'll probably check that out. And then Wednesday, I think I'm going to be having a conversation with Jaren from Jarenism. We're going to be doing a cosmological recap, going over the celestial theodolite and TFE and the old Antarctic sun situation. And so tune into that. And then on Saturday, on that Saturday, on the 15th, at I believe what would that be? 2 p.m. Eastern, I think it is. We'll be doing Shane and I will be having a debate with some English speaking Czech lads that say that they have refutations to the celestial theodolite, that our premise is malformed, etc. So we're going to have a nice little debate with them. So tune into that on Saturday. So let's see. Wait, Sunday, Monday, Tuesday, and Wednesday. Yes, that's correct. And then also Saturday, and then Friday, of course, we'll do Twitter community night and or something with the Flat Earth Gang over on Clubhouse. But if you have Twitter, follow my boy Brian Sweet. He hosts weekly Friday sessions for Flat Earth community, for the Flat Earth community. Don't see all the events. Oh, I'll link you, Coco. My events are on my YouTube channel here. So every event for the next week is planned out here, except for the community space. I got to add that one, but that'll be on Friday.
That's interesting. You're talking with Jaren. So is that going to be on his channel?
Yeah, he's gonna stream it, and I'm gonna stream on mine. Yeah, man.
So he's still open discussing all these things and considering.
I mean, he's at least open to it with me. I've maintained a good relationship with him, and I've been I'm not gonna not be his friend because he believes the Earth's a globe now because he went to a place and saw a thing he didn't expect. So we're still cool and stuff. And I was really wanting to talk to him about the celestial theodolite because I think it illustrates our point, in a meaningful way that's more than just like saying nuh-uh, you know what I mean? So, I really want to go over it with him. So, and he's open to it, so that's awesome.
Nice. Yeah, that sounds good. Yeah, I don't.
And when is that happening?
That'll be Wednesday at 3 p.m. Pacific.
Nice.
Cool. Yeah, I checked his channel a little while ago. It doesn't seem like he does as much content on the Earth. Like, I guess he's doing these like trivia things, but
yeah, and I think he started a new channel called Interestingism. So yeah, I think he might be doing stuff on that. I haven't kept up with like other flat Earth channels in a hot minute. I'm super busy with stuff, so not really sure what he's been up to on that one.
Oh, okay. Yeah, I had heard about that channel. Interestingism. Oh, okay. Yeah, I see he's doing stuff here. Okay, so yeah, so he kind of shifted over to this channel basically for his kind of more of the discussions on these topics. It looks like yeah, Charlie Kirk. And so you're going to be on so it's going to be on the Interestingism or on his channel, the one that you'll probably like multi-stream it?
Yeah, good question. I'm not sure. I would assume it'll be on the Interestingism one though.
Cool.
All right, lads. I'm gonna hop off. If anyone wants links to the research and stuff that was done, here's some Canva links for the Prezi presentation. Oh yeah, I should have put that in the thing. Here we go. History of wave invariance. So here's all the slides, and then I cited everything. So you want the sources there. They're all in the thing there. And then of course there's the Space Audits Obsidian webpage, which has the latest and greatest updates on celestial theodolite, the new Prezis and stuff. All the old stuff is moved to 99_old. But the new relativity thing with the wave invariance is right here. So you can get the sources and images from this as well, if you need that. And of course, if you need any of those sources, because sometimes they're hard to find, hit your boy up. I will send them to you. No problem. I have them all on my Zotero. Oops. Close that. All right. And if you guys are out there researching in the streets, highly recommend you figure out how to use Zotero. It's fantastic for managing all your sources and stuff and categorizing everything. And then when you go to link someone a source, it's always available to you at a few clicks.
Do you find that people get mad at you when you cite your source?
Yeah.